Let's take a look at the MOSFET device now. We have an N-type source and drain, and P substrate body is shown here. The P substrate is tied to the lowest voltage, that is the ground, lowest voltage available on the system, that is the ground, 0. Its symbol is like this. So the arrow, so you have to be comfortable with the arrow notation. The current flows from drain to source, right? So gate, if your current direction is determined, then the VGS is determined, right? So voltage across VGS actually determine the overall characteristic. So MFET is shown in here, and the PFET on the right, bottom right here. The thing that you have to make sure is the body connection actually is done through the body contact here for each. So MFET and PFET actually 4-terminal device with NMOS device, and PMOS device, the body. So drain, source, and gate. Current flow from drain to source in NMOS device. In PMOS device, current flow from the source to drain. The source and drain. This is the gate. So you have to identify first where the current direction is. The current direction is basically depends on the voltage relationship. The current flows higher voltage to low voltage, right? So the PMOS has the higher voltage on the source than the drain. Let's put more closer look at on the PMOS device. So PMOS base, the body is tied through the N plus, and PMOS body is N-type, the NL. So for the PMOS, we have the parasitic diode here. For the NMOS, we have a parasitic diode in this direction, right? This is the P-type and N-type. So all these parasitic diodes must be turned off, right? To do that, the P substrate is tied to ground. For the PMOS, the body is NL, so that is tied to where? VDD, that is highest voltage available in the system. Then make sure all PN junctions and junctions are off. So in MOSFET device, we are not relying on the PN diode operation, unlike the BJT. So all the PN junction must be reverse biased. These are example of the variety of the symbols that represent NMOS and PMOS device. So you guys need to be comfortable with those symbol notation. So arrow notation here shown in here with the body connection. Without body connection here, we assume that body is tied to GND for NMOS, VDD for PMOS device. So with bubble notation, we have this is widely used in digital, mostly used. in digital design, or digital designers are more comfortable with this notation. So here with the bubble here on the gate, that represent PMOS device. For digital designer, they treat the transistor more like the switches. So switch on and off condition is represented by this bubble or no bubble kind of a situation. The thing that you have to really understand that is that the drain and source is determined by the current direction, right? MOS, current flow from drain to source, and for PMOS, current flow from source to drain. So this is a higher voltage, a lower voltage. Right? All these must be higher voltage, and source below those are lower voltage, to make sure all the current from top to bottom. This current direction is quite identifying current direction is quite important. So for MOS, so you have to understand later or now. So drain is output side, put usually. So for the MOS is for the pulling down the output, pull down purpose, and PMOS is for the pull up current. Right. And also for small signal analysis like a transconductance, you can analyze that, and so you know that equivalent resistance. So for the MOS, resistance looking into the source node, let's say for example REQ. For PMOS also, impedance looking into the source, that is REQ here. Such REQ is defined by 1 over GM. So GM is the transconductance. But if you look into the drain side, that is RO, for example, RO is like a small signal RO. So here MOS also looking into the drain side, that is RO, then the small signal resistance is like that. So the small signal resistance, equivalent resistance, greatly determined by the whether that is source or drain. Depends on either whether source or drain. This is a very important feature that you have to understand. Although the device itself, for example MOS and PMOS, are symmetric, depending on the current flow, depending on the current direction, the electrical property is greatly different, right? So you have to identify, whenever you see the circuit, you must be able to identify where that the current, actual large signal current flows, the direction, what is the direction of the current. That's the key, the first step to analyze the circuit in the first place. Let's take a look at and study the behavior of MOSFET when we drive the gate voltage higher. So in this MOS device structure, we tie the body to ground, and drain side is, let's say, connected to 0.1 volt, very slight voltage, so that the current can flow if there is the channel happen between source and drain. Let's say initially the p-type has lots of hole here, and n-type has lots of electron on the outer shell. For now, nothing is happened, but if you start increasing the gate voltage, then the electron is attracted, the positive charge is attracted on the right hand side. Positive charge is attracted on the top gate plate, and negative charge is attracted on the surface. This negative charge is filled in the hole, so initially negative charge is trapped by the hole, so it forms depletion region. So this is called the depletion region. Why this is called the depletion region? Because the mobile carrier is depleted. So now it's like a void state of the mobile carrier on this region. Now if you even drive the even higher gate voltage, before we move on, even higher, if we drive the even higher voltage, then the free electron attracted more on the surface, so this can see the voltage difference between the drain and source. So current flows from the drain to source because of the voltage difference we are seeing here. So sheet layer of the electron actually forms the channel. Through this channel current can flow, and this p-type device is changed to n-type on the surface. So this condition is called the channel inversion. So channel inversion. And this channel inversion happen if the Vg is greater than equal to a certain threshold voltage, that is called, let's say, VTHN. In modern technology, that is around 200 to 100, depending on the device type, it's different. 100, less, around 100 to 300 or few hundred. All these all these are different for devices. The VTH is like let's say around 100 millivolt or 200 millivolt or 300 millivolt. We see variety of devices in actual design. So once this kind of a channel happen, we can see that this device structure as the linear passive element, like we can model that there is between gate and channel, we see the some amount of capacitance COX, and also between channel and the P substrate there is just some gap through this depletion region, right? That causes also the depletion cap there. Also, there is a junction, reverse junction, the PN junction, that also causes some amount of diffusion cap through the reverse diode. Off-state diode also causes the capacitance. In the previous example, we just limit our case is VDS is around 0.1 volt. In that case, if we change VDS, the current changes linearly like this. So if you zoom in this region, this linear variation is set by a certain VGS. if you start increasing VGS through the device, let's say N plus and N plus, VGS, large signal current, VGS. If you increase VGS, then more current. So for the fixed VDS, like VDS equal 0.1 volt, if you increase the VGS, then more channels, more electrons are attracted on the surface. That increase the current level like this, right? Depend if you increase VGS. It looks like a small resistor, a variable resistor, depending on the VGS. If you recall this, this region is called the triode region. So we can write down the equation for triode operation. ID equal mu n COX W over L VGS times VDS half VDS square. We'll not spend our time to drive this. This is already covered in undergraduate course. If the VDS approach to near zero, we can take it out, the square terms. It can be more simplified like this. So the relationship between ID and VDS will be what? VDS over ID is, we can define that is on resistor through between drain and source, right? This channel, the resistance through this channel shows some resistor R-on. Such R-on is found by like this. So changing VGS, you get the higher VGS, you get lower on resistance. As you can see in this example, you see that higher VGS, that the slope of this curve is 1 over R-on, right? So higher VGS, you increase the slope, meaning you get the lower resistor. Now if you increase even further VDS, even higher, so there is some point that the current doesn't increase, some non-linear, so the current is compressed here. Current is compressed, saturated for larger VDS. Why this current is saturated? We will see it later. So this kind of a current saturation causes some nonlinearity. So in triode region, it is quite confusing sometimes which one is source and drain. As I mentioned before, the source and drain in triode region depends on the current direction. If the current flows from left to the right, that means the higher voltage drain and source. If the current flow right to the left, that means the drain and source. Why it is important to identify this as well? Because the on resistance, variable resistance, depends on VGS, gate voltage versus gate source node voltage, right? In this case, current flows drain to source. In the other case, like if the current flows left to the right, then the right hand side is the source, and the voltage on the source is important to determine that the resistance. Okay, so the triode region is kind of a voltage controlled the resistor. In previous triode region, we started increasing the voltage VDS from 0.1 volt to even higher. So if we start increasing the VDS, the ID increase linearly. At some point, it's like a compressed. Let's take a look at this operating point Q. What is happening? When VDS is equal to VGS minus VTH, and on this here, bottom here, so VD drain voltage even higher, so the gate voltage in VG, so voltage between gate and drain VGD approach to VTH at that point, this voltage difference, meaning at this point the channel inversion condition start violating, because the channel inversion happen only when gate voltage versus that surface voltage difference is greater than VTH. Then we see the channel inversion. But if you start increasing and get to this voltage, there VGD difference is less than VTH, the channel inversion disappear. So we see this kind of profile, triangular electron density profile. At the tip of the triangle point, we are saying this is a pinch up happen, so channels start disappearing at the edge of the drain. If you drive the even higher drain voltage, then this pinch up point is retracted toward the source node. Why? Because if we increase this drain voltage, we are even applying higher the reverse voltage through the diode. In the diode, we have in the reverse bias, the diode, having higher reverse voltage will result in more depletion region. We have a here depletion region gets wider as VD goes up, right? So this once that pinch up happen and the VDS goes up, then this the electron profile doesn't change. If you plot the gate and substrate voltage difference on this axis, so from the source node we have a VGS, large VGS that is greater than VTH, so we have a strong inversion there. As we moved our point on the surface, the voltage will go up and up, so that the voltage difference between gate and surface will go down. So at that last point, when the channel inversion disappearing point, that is the VTH, the difference where the gate and surface pinch up point, the difference will be VTH. So that this is the minimum voltage that require to make that channel inversion. So once this pinch up happened, the overall current doesn't change. It's fixed. It looks like a resistor. All right. So we define this critical point VD set. Once the VD set is defined by VGS minus VTH, that is we call V overdrive voltage or V effective voltage. In some other tools inspector, it says VGT is something that has a similar concept of the overdrive voltage. So this, once the overdrive voltage is defined, that if VDS is greater than VD set, the output current is saturated. It is constant current. So this looks like a current source. Okay. And from the triode equation, if you remember triode equation, ID equal to mu n cox W over L VGS minus VTH VDS minus half VDS square. So at the boundary between triode saturation region, VDS is equal to VGS minus VTH. So if you plug in this equation onto the first equation, then you will end up having this kind of a well-known saturation equation. From this, current is only determined by the VGS. So this is voltage controlled current source. Each current is related to scale law, scale function VGS minus VTH scale. So ID is, what is important is ID is proportional to width over L times overdrive scale. Right? So what determines their current is the overdrive voltage, right? In undergraduate course, in saturation, we assume that current is not changing, even for VDS variation. But in reality, we are seeing some variation on the current because of the second order effect. The second order effect that we can think of out of this device operation is shown in here. If you have a higher VDS here, if you change, so this slight curve, meaning that if you have a different VDS, you will see different current level. Why we have a different current in actual device? Because if you have a higher voltage, then you will get wider depletion region, right? You are actually modulating depletion region with more drain voltage, higher voltage, and also you are getting more strong electrical field. If you make this drain higher and higher, then your depletion, reverse bias is getting even higher and higher, and more depletion region. So depletion will get widened. Region gets wider, and the electrical E field is stronger. So your actual profile changes, current profile change, density profile changes, right? The change in profile actually changes the current. You can think of the distance of the channel is this distance, effective channel length. You are having wider depletion region, you will get the more narrower effective channel length, right? So more current can flow. Now that actually results in the final current variation on the saturation region. The slope of this guy is 1 over RO. We will see in more detail how we equate this number and find this number later. In undergrad Of course, we modeled the device using the ideal scale law model. It was kind of a clear distinction between saturation region and triode region and off state region. So we define the off state when the VGS is below the threshold voltage. But there is a slight ambiguous region, like there is some ambiguity related to here. If you zoom in this region more closely here, so it isn't like this. So I'm meaning, so below VTH, for example, there's just still current flows, right? It is not like this ideal scale law model, IDS versus VGS. There is some non-zero current flows. This curve is following exponential equation as shown in here. IDS is proportional to exponential VGS over NKT over Q. This is very similar to diode equation. So if you plot the current in log scale, it actually follows the log characteristic. The linear in log scale, meaning the exponential function. In strong inversion case, it follows the scale similar to scale law model, like VGS minus VTH square, that is proportional to IDS. But even higher VGS, velocity is saturated, meaning the current is no more scale relationship to the VGS. It becomes more linear to the VGS over VTH minus VTH. So IDS is linear, the proportional to the overdrive voltage. So current does not increase as much as the scale law model. So it's just saturated. Why? Because the too much the higher voltage VGS, for example, here. So if you drive the higher voltage, then you get more intense electrical field. The electron was supposed to move from source to drain freely, but because of the higher and higher electron, the electron cannot move as fast as because it is bumping onto the surface, and amount of current the current flow is hindered, and current flow is kind of somewhat hindered by this strong electrical field, so the current is saturated. In this example, it is demonstrating how to quickly identify region of operation. So first, we are assuming that every VGS is greater than VTH, so that the channel inversion happen. So channel inversion, channel is on at least, right? So if the drain voltage is higher than gate voltage, this is saturation, and then if the gate voltage, drain voltage is going lower and lower, from higher to lower voltage, down and down again, and at some point it is going into triode region. At the boundary of the triode and saturation, the voltage relationship and gate and drain is only VTH difference, so VGD is VTH at the boundary, right? This means the VDS is equal to VGS minus VTH. You guys always remember only this equation, but you have to also know that this equation as well, because that is more insightful when you identify the regional operation. So you have to understand those two equations more freely. For the PMOS, it's similar. So if you have so VSG is greater than VTHP absolute. So typically VTHP is represented by the negative number. So for easier circuit analysis, we place absolute the VTHP. So if the VSG is greater than VTHP absolute, then the channel is on. Channel is inverted. Now let's look at the difference between gate and drain. If the drain voltage is going up and up, here at the drain voltage is same as gate. If the drain voltage is lower than gate voltage, then definitely it's in the saturation. If the gate and drain is the same voltage, then it is still saturation. But if the drain voltage is going too high, so that the voltage difference between DG is equal to VTHP absolute, then it's at the edge of the triode region. So this equation, you can also see that VDS is, in terms of VDS, is the same as VDS minus VGS, the same as VSG minus VTHP. Okay. So this, in this case, VSG. So VSD, this is source and bottom is drain. VSD approach to what? VSG minus VTHP. So this is the voltage relationship, terminal between terminal. We are getting this kind of a voltage relationship. On the MOS as well, we have a VSG, a VGS between gate and source. Between VDS is equal to VGS minus VTH. So if the drain and gate and drain voltage difference is like this VTHN, then you are seeing this terminal voltage relationship. So you have to be comfortable with calculating the voltage drop over terminals, and you guys need to quickly identify the operation region. It needs more practice, you guys, if you want to be more able, if you do want to be the high-level design engineer, you have to understand and quickly get this operating region easily. Otherwise, you cannot design good and reliable circuits. This is very important thing. So you have to train yourself at home all the time. Okay. We will quickly review the small signal parameter like both transconductance in ideal square law model. So ID equal mu n COX W over L VGS minus VTH square, that is mu n COX W over L V over drive voltage square. So from this equation we can derive the GM, transconductance, that is round ID over round VGS for the given VDS condition, for the fixed VDS voltage. So if you know that if you think of the ID versus the VGS relationship as an ideal case like this. So at the one operating point, we can, this is pretty non-linear, so you can linearize the slope. Although this is the scalar model, at this slope we define the slope as GM, transconductance. So that is in small signal model we can model like this. Plus minus VGS actually determine I times GM ID, and GID equal to GM times VGS. This is the drain and this is source. This is the gate. So at one operating point we can assume that. So this is for in saturation region equivalent model in small signal model, in saturation small signal model. To extract this small signal GM transconductance, we have to identify what is large signal current and VGS, right? That must be first identified, and then once that is determined, then we take the derivation from here. Then first equation for GM is directly from square law model from here, this equation, and that gives us mu n cox W over L times VGS minus VTH. This is the first equation for representing GM. And also, you based from this, let's say this first equation, and the second equation can be also derived from the original square law model. How we will get? So we replace the VGS. So we know that VGS minus VTH is equal to what? ID over mu n cox W over L square root, right? Plug this relationship onto the 1, that will give us the 2, right? Now we can another equation, third equation, 2ID over overdrive voltage here, that can be derived by replacing mu n cox relationship W over L, this guy, where we get from here to there. So we know that mu n cox W over L is equal to, also here, sorry, half mu n cox. So this guy was what? Half. I took out the half here to try, right? Here 2i, I was missing that 2, factor 2. So here mu n cox W over L is what? So 2i ID over V overdrive square, right? So we plug that onto the 2, then we will get this equation. So rewriting in overdrive voltage 2 times 2ID over V overdrive voltage square. So these three equations represent the transconductance. This is very important to remember all these three relationships. So you have to identify when we do really use this equation, in under which condition we will require to use. We will see quickly some of the cases shown in here. Let's take a first example. W over L is constant. What if you have a transistor here and the size of the transistor is fixed? You are modulating VGS, you are changing VGS, and drain voltage is higher than VD set, so meaning in saturation. So we are assuming the device is in saturation. To increase the VGS, then what will happen? We will know that the current will increase by the square law model. What about the GM in that case? If you want to know the GM of that, so what? For the fixed W over L, what you are changing is VGS, right? In that case, the linearly GM is increasing according to VGS. So linear increase in GM. That's the other case for W over L is constant case. No, I'm sorry. W over L is constant, but the ID is varying. For example, in case you you want a W over L is constant, you want to change the current through the device. So ID here, the current through this device is ID, right? So we assume that device is in saturation. In this case, if you start in, so for the ID, initial ID will be set up by the device size, and each overdrive voltage will set up by the depending on the size. That will be overdrive here. If you start increasing ID, then it will flow more current, right? So I remember ID mu half mu n COX W over L VGS minus VTH square. If you increase the VGS, more current flows. So if you start increasing ID linearly like this, then what you are getting is the VGS changes according to scale law model here, right? So the GM, if you want to look at the GM variation for this case, you have to look at the the second equation, right? For the fixed current, you are changing, for the fixed device size, you want to change the ID, you want to see how the GM varies like this, right? So it is proportional to square root of the ID. The last case is that in this case was the ID was the changing, but the last case we wanna do some experiment that ID is fixed, but you want to change the W over L device size. Then what will happen? If you change device size, you know that the overdrive voltage will change, right? Gate, because the current density changes depend for different device size. If you have a different size, then the VGS changes, right? Change in VGS means the different overdrive voltage also changes. So the relationship between GM versus overdrive voltage is what? Everything else is fixed. The ID is fixed. So for the given ID, the relationship is like that, to ID over overdrive voltage. From this equation, this last 3/3 equation doesn't have a mu n COX W over L, right? All these physical parameter is missing. Only electrical parameter like ID and overdrive voltage is related here. So it is more insightful to use the third equation, but in some cases it is more useful to use one or two, equation 1 and 2, because depending on what is fixed and what is constant, what is the one that you want to make it maintained. So depending on that variable, we have to be able to freely find and choose one of those three equations. Okay, so you guys need some practice, and this is very important. Three equations we have to remember. Let's take a quick comparison on between BJT small signal model and MOSFET small signal model. For MPN shown here, we have a saturation region below VC 0.2, less than 0.2, and above VC we have an active region. In MOSFET we have a saturation region when the VDS is greater than VD set, that is equal to V overdrive voltage here. Saturation region is different, has different meaning in BJT and MOSFET. So in the BJT, we don't want that BJT device in saturation. We want that to be inactive. But in MOSFET, we want that to be in saturation for current sourcing. So in active region of the BJT, we can model the input as R pi, that is resistive, because the voltage and current, there is non-zero current on the base because of the diode through the base, right? Between base and emitter, there's a forward bias that has this kind of a relationship. So 1 over IB is the IC over beta. The IB versus VD, the diode voltage relationship, there's some finite slope there. The slope is 1 over R pi. So small signal resistance there between base and emitter. That GM times V pi, that results in IC collector current. It can also represent in current gain beta, so IB times beta, that determines the collector current. On the other hand, the MOSFET, there's no current gain beta. It only have a transconductance because there's no current going into the gate. IG equal over 0 in DC. Definitely, if you consider the capacitor at the input, there's some non-zero gate current, but in DC level, DC model, so we will get the ideally zero gate current, so there's no beta can be defined. So we have a transconductance GM here. So comparing between left and right, so MOSFET is simpler in terms of the absence of R pi shown in here, but for the circuit analysis wise, if you are familiar with the basic RLC circuit analysis, it will be not that difficult to consider that R pi in BJT and non-zero IB current.